Welcome to Study Loop.
So for this question, start by looking at the problem and determining that in this point, when using the second law, sum of the forces equals mass times acceleration in the y direction because it's going down. So this is on the inclined plane, and at this point, the acceleration is 0. So you can also find the normal force, which is equal to weight times cosine theta, or cosine 30. And we can determine that it is equal to 8.5 times m. So when you find the frictional force, you can determine that it's just the coefficient of the kinetic friction as it's moving, which is 0.2, multiplied by that normal force, 8.5 times m, and you get 1.7 times m for the frictional force. Now the work done by the friction from A to B just use this equation, work times sine 30 minus friction, let's call it FR, 1, and you multiply that by the distance. So you can simplify this down to mg sine 30 minus 1.7 m, which is the friction force we found, or the work done by the frictional force done we found earlier. You multiply that by 6, which is d, and then we should get 19.23 times m. So once it hits the surface level, there's now a new normal. So once we're here, we can take this new normal, the second normal force, and that's just energy because it's on a flat surface. And it's 9.81 times m. In this case, when you find the frictional force, second frictional force, you use the same coefficient of friction, and now you multiply by the new normal force. That should get you 1.962 times m. Now, to find the work done by the friction on this flat surface, let's take the work done by friction 2, negative, multiplied by the distance, x, that's 7. So when we plug in the numbers, we know it's 1.692 times n times 7, and that should get you negative 13.734 times n. So when looking at this, you have A, kinetic energy A, which is the 1/2 mv squared equation. Mass times velocity squared. We plug in the values we have. That's the velocity is 1. So it's 1 times n times 1 squared, and that is 0.5 times m. This is kinetic energy A. Kinetic energy at C at the end. Same equation. Yeah. We don't know the mass or the velocity yet, so we can just leave them as variables. we're assuming that no energy is lost at B. So using the conservation of energy, we would have this equation. It's just the work kinetic energy at A, and this is what we're looking for is kinetic energy at C. And we can find that by plugging in what we already know. So we found before kinetic energy at A, 2.5 times m plus 19.23 m plus minus negative 13.734 m equals 0.5 m VC squared. So since we have almost everything we need, the m's will cancel out. And now we just have to solve for VC. And if you solve that, you just add up or subtract these numbers, then divide by 0.5 on each side. You should be able to isolate VC. Get VC squared equals 11.992. When you square root that, you get the velocity at C equals 3.46 meters per second. That's the final velocity. Now to find the distance, we want to find the work done by the friction on the belt. But first we're going to find the frictional force. It should be the coefficient of friction times the normal force, which is equal to 0.2 mass times gravity, equal to 1.962 meters. Now, to find the work done, let's multiply the negative friction times the distance, the length of the belt. You get negative 1.962 times m times x belt. Now using conservation of energy, using the kinetic energy of C that we found earlier, plus the work times the kinetic energy of the belt, negative 1/2. Just plug in the values that we know. The ones we don't know, we keep as variables. Once again, we divide through by m. The m's cancel out. We don't need the masses. And we just plug in what's left. Once you get that, you should be able to solve for this variable, x belt, and you should get 2.03 meters.